Hey guys, this is part 2 of statistics. We're still in chapter 4. We're going to talk about the t-test and some other statistical things. Let's get started. I'm going to start this video by asking you, how confident are you that the data you're going to produce in the lab is correct? We just talked about in the previous video how your true value can never be found because we would have to run an infinite number of samples. And we've also learned that statistics can actually help you with getting closer to the actual mean, the true mean. Statistical theory can also help set limits around the mean or around the average where you should find the true mean, the population mean. And this is something that we call confidence intervals, and I'm going to name it CI from now on. Confidence limit, this is what defines, it gives you the limits, it defines the interval, and the confidence interval is actually the magnitude. It gives you the range of values within which there's a specified probability of finding your true population mean. And here I'm showing you the definition that I just said. CI is a range of values within which there's a specified probability of finding the true average. And the equation for confidence interval is shown right here. That's mu, which is the population mean, is equal to the average plus or minus TS over the square root of n. Now T is the student's T, which we're going to talk about in a little bit, and I'm going to show you the table that you need to use when you use this equation. N is the number of measurements, and of course S is your measured standard deviation. The confidence interval is a range, remember, so we say that the population mean is likely to lie within a certain distance from the measured mean, that x bar. And remember, you have a lower limit, which is x minus TS over square root of n, and then the upper limit, which is x plus TS over the square root of n. All right, let's do a problem. This is the example used in your book. It reads, in replicate analysis, the carbohydrate content of a glycoprotein, which is just a protein with a bunch of sugars attached to it, is found to be 12.6, 11.9, 13.0, 12.7, and 12.5 grams of carbohydrate per 100 grams of protein. Find the 50% and the 90% confidence interval for the carbohydrate content. This question is really simple. All you have to do is use the equation that we just talked about. Its population mean is equal to the average plus or minus TS over the square root of n. First thing you got to do is find your average. So if you do that, you should get 12.5. The next thing you do is find your standard deviation. And once you do that, you should have 0.4. The next step is just to find what is the t-value, and we do that by using the table in your book. Now, let's do the 50% first. And we see that we have 5 measurements. So when we go to the table, we have to go to the 50% column, and then we use the degrees of freedom. So we don't use 5, we use n minus 1, 4. So you see that the number that you use is 0.741. So that is what you plug back into your equation. So it should look something like 0.741 times 0.4, which is your standard deviation, divided by the total number of measurements, which is the square root of 5. If you multiply and divide all that out, you should get 12.5, that's your average, plus or minus 0.1. So what does that mean? That means that there is a 50% chance that the true value lies within that interval that you just calculated. So the value could lie anywhere between 12.4 to 12.6. If you do the 90% one, all you have to do is use the number for the 90% confidence interval, and that would be 2.132. So you go back to your equation and you do 2.132 times 0.4 divided by the square root of 5, and that should give you 12.5, which is your average, plus or minus 0.4. So that means that there's a 90% chance that the true value lies within the range of 12.2 all the way up to 12.9. So this is very simple. All this is trying to tell you is you are confident that the true value lies within there. Even though we only take a limited number of samples, you can use the confidence interval to actually find where that true value actually is. The test yourself asks you if your average and your standard deviation stay the same, but instead of 5 values, you use 10 values, what would be your 90% confidence interval? So everything stays the same. The only thing that we're changing is the degrees of freedom. So we go all the way down to 9 at 90%. You see it's 1.833. So you plug that in to the equation and you should, so it would be 1.833 times 0.4 divided by square root of 10, because it says that it changed the number of measurements to 10. And that should give you 12.5, same average, plus or minus 0.2. And notice that the more measurements you do, the smaller your interval gets at a better confidence level. And that's true always. Okay, let's move on. So how can you improve the reliability of your measurements? Well, I just mentioned it. If you make more measurements, then that's going to give you smaller confidence intervals. Duh. So, in other words, being 90% sure your answer lies within the range of 62.3 plus or minus 5 is way better than if you say that your answer lies within 62.3 plus or minus 1.3. Of course it is. The range is smaller, so you know that your value lies within a smaller interval. It's better. So the t-test equation tells us that to reduce the confidence interval, we must either make more measurements, which is probably the easiest, or decrease your standard deviation. The only way to decrease your standard deviation is to improve your procedure, which sometimes can be really difficult. Another way is just to make more measurements. Let's move on. What else can the student's t-test do? Well, it can be used to compare two sets of measurements. In other words, it could answer whether or not the averages from two different sets of sample data is the same or if they're different. And that is the equation that you would use if you wanted to answer something like that. It says T is equal to the average of the first set minus the average of the second set absolute value. And the reason they put the absolute value is that that number is always positive, divided by S pooled, which is a standard deviation pooled, and I'm going to show you what that is equal to in a second, times the square root of the number of measurements in the first set times the number of measurements in the second set divided by the number of measurements in the first set plus the number of measurements in the second set. It's a bunch of letters, but we know all of these values already. Now S pooled, I'm showing to you right here. And again, you see all of the different variables you use here are the variables you know already, or you would know because the problem would give you all of this information. So this is not a hard equation, it's just you have to have all the pieces of information to be able to plug into here. And how do you know if they're the same or not? Well, if the t that you calculate is bigger than the t that's in the table at 95%, it has to be at 95%. If the t that you calculate is bigger than the t in the table at 95%, then the difference is significant. So that means that the means are not the same, and you should be wary of those two, comparing those two data sets. Do you guys remember the F test? Remember that we did the problem that compared the old instrument and the new instrument to see if the data they were obtaining was significantly different, and remember that the answer that we got was that it was not significantly different. Why don't we try doing the t-test, which now compares the two averages, not the two standard deviations? What do you think you would get? Well, your book does it for you, as a matter of fact. And if you look on page 85, they actually calculate S pooled first. So in the table 4.2, where we had gotten the original data from, the average of the first set was 36.14 and the average of the second set was 36.2. And we knew the number of measurements. The number of measurements for this set number 1 was 10 and the number of measurements for the set number 2 was 4. The standard deviations were also given to us. All they did is plug everybody in. So they ended up getting the square root for S pooled, square root of 0.28 squared, parentheses 10 minus 1, plus 0.4 squared, parentheses 4 minus 1, over 10 plus 4 minus 2. They multiplied all that out and they got 0.338, which of course ended up being 0.34. And then they plugged that number into the t-test equation and they multiplied all that out and they got 0.30. Now the calculated value of the t is 0.30. When you look at the table, which I believe I have here, when you look at the table of the number of total measurements you made, which was 12, because remember it's N1 plus N2 minus 2, that equals to 12. It lies between 2.228 and 2.131, listed for the 10 and the 15 degrees there. Because the T calculated, which was 0.30, is less than the T in the table, then the difference in the mean is not significant. And you should expect this, because the difference is less than the standard deviation of either measurement. All right, let's move on. The last thing I want to talk about in this video is how do you detect outliers? For example, if you have a group of 4 people that get these measurements and all of them pretty much are in the range of, 10 and 9 and 11, but then you've got one, which is Cheryl, and she gets 7.8. Now, how do you know if you keep that? Is it a real measurement, or was it a fluke that shouldn't be incorporated into the rest of the measurements? We have a test that can tell us that, and it's called the Grubbs test for bad data. The equation is right there. It says you take the absolute value of the questionable value minus the average, and you divide it by the standard deviation. And if what you calculate is greater than what the table is, then that point should be discarded. So the average, if you take the average of all those numbers, it's 10.16. If you take the standard deviation of that, it's 1.11. So what you would do is take the absolute value of 7.8 minus 10.16 divided by 1.11. That should give you 2.13. When you look at your G table, the G table says that it's 2.285 for a total of 12 data points. And that's what they have. They have a total of 12 data points. Here it's not a degree of freedom. Here it's just how many data points you have. So that's 12. And the G calculated is 2.13. So that point is actually good. You should not discard it. You should keep it. You should retain that 7.8 and use it in your statistical measurements. So that's pretty much it for this video. We've learned a couple of things. We've learned how to do the confidence interval. We've learned what a t-test is and what a t-test can do. By that I mean it can compare averages of 2 different sets of data points. And we've also learned how to do the Grubbs test. Next thing I want to talk about is finding the best straight line. So calibration curves and all that stuff. All right, guys, I'll see you later.